Hello everyone. I'm glad you could join us. Imagine a world where life could exist without water. Strange, isn't it? No rivers, no oceans, not a single drop, and yet life somehow finds a way. So settle in, let your body relax, and let your mind wander as we dive into 12 fascinating conspiracies that will take us to the edge of the unknown. Chapter 1. What does life really need to survive? Life as we know it always begins and ends with water. Every biology textbook opens with water as the defining element of living systems. Every laboratory experiment begins with water before chemicals, before energy, before cells. Water is more than a substance. It is a medium, a cradle, a silent architect of life. It flows in rivers, pools in lakes, rains from clouds, and courses through the smallest cells. It is the constant we take for granted, so natural that we forget how strange it is that life as we understand it would be impossible without it. But water is not the only possibility. It is the story of life on Earth. If we leave this story behind and look deeper into the vast reaches of the universe, could something else fill the role water plays for us? Could life exist without water at all? Could there be other liquids, other chemistries, other conditions where life finds a way? To answer this, we must step away from human assumptions and look at the most fundamental requirements of life. When stripped to its essence, life is not defined by form but by function. Life is an organized system that maintains itself against the tide of entropy. It gathers energy from its surroundings. It repairs itself. It reproduces or passes information forward. Every living thing we know follows this pattern. The chemical details may vary, but the purpose remains. Life is persistence. Water happens to be the solvent that makes this possible on Earth. It dissolves minerals. It enables chemical reactions. It regulates temperature. It creates a home for molecules to meet and transform without destroying each other. But it is not the only way to achieve that. Life needs a solvent, an energy source, and time. A solvent is the liquid environment where chemistry happens. For us, that is water. But elsewhere in the universe, other liquids could serve the same purpose. Ammonia, methane, formamide, sulfuric acid, even exotic combinations we have not yet imagined might act as solvents under the right conditions. These substances could dissolve nutrients, transport molecules, and host the complex chemistry needed for life. They would look strange to us. They might be invisible, glowing, toxic, or freezing. But to life evolving there, they would be normal. Energy is the second requirement. On Earth, it comes mostly from sunlight, but also from geothermal heat, chemical gradients, and biological energy stored in molecules. On other worlds, energy could come in forms we cannot yet predict. A planet deep under ice might rely on heat from its core. A moon bathed in radiation could use that radiation to power metabolism. A drifting body in interstellar space might harvest cosmic rays. Life is not picky about energy as long as it can capture and convert it. Time is the third requirement. Complexity does not appear instantly. It is the slow result of countless small changes repeated over unimaginable spans of time. Evolution is patient. It takes millions and billions of years for simple chemistry to become living organisms. In places where conditions change slowly, even harsh environments may give life a chance. On Earth, life is remarkably adaptable. Microbes survive in boiling acid, deep underground in complete darkness, inside Antarctic ice, and even inside nuclear reactors where radiation levels would destroy most life. These organisms are proof that life does not cling to a narrow range of conditions. Life simply adapts to the conditions available. That adaptability gives hope that water is not the only path. The universe may have filled itself with strange seas where life thrives without a drop of water. On Titan, a moon of Saturn, there are lakes of liquid methane. On Europa, beneath kilometers of ice, there may be oceans of liquid water mixed with other substances. On Venus, there are clouds of sulfuric acid. Each of these could be a habitat. To us, these places seem inhospitable, but that is only because we see life through the lens of Earth. Life elsewhere may not see danger or toxicity as we do. Imagine a world colder than anything on Earth. Air there could be a solid. Oceans could be methane or ammonia. A being in such a world would not need warmth to survive. Its metabolism would be slow. It might think in years rather than seconds. It might live its entire life drifting through an ocean of strange liquid, never needing more than the chemical balance of its environment. Perhaps life does not even require a solvent as we define it. Could there be life based on entirely different chemistry? Could life exist as self-sustaining energy patterns, as crystalline structures, as networks of molecules without a liquid base at all? That is the deepest question of all. If we search for life beyond water, we are searching not just for another biology, but for another definition of life itself. Our question changes then. It is no longer can life exist without water. It becomes what is life. What would it mean to be alive without the cycles of water, without the familiar rhythm of breathing, eating, and reproducing? Could life exist as slow chemistry in a frozen sea? Could it drift in the clouds of a toxic planet? Could it survive in the vacuum between worlds? Could it be something we have never imagined because it does not think in the language of life we know? Perhaps somewhere in the universe there is life without water, a strange, invisible life that moves in a solvent we cannot touch, breathes chemicals we cannot smell, and persists in ways we cannot imagine. That life would prove that life is not a singular miracle tied to a single substance. Life would be a pattern of persistence that can emerge anywhere, wherever the right ingredients come together. Water is not the definition of life. Water is one chapter in its story. Somewhere out there, the story may have been written differently. Somewhere, there may be life that never knew water and would not understand why we think of it as essential. That possibility changes everything. It makes the universe a far stranger and more wonderful place. If we truly want to know what life is, we must be willing to look beyond water. We must look for life as chemistry, as persistence, as the slow work of complexity building itself against the cold and chaos of the cosmos. We must look for life as it might exist anywhere. Life needs only a chance and enough time to take it. Chapter 2. Could ammonia replace water on other worlds? Ammonia is one of the stranger liquids we know of. It does not sparkle like water. It does not support life as we know it here on Earth. Yet ammonia has properties that make it an intriguing candidate for life beyond our world. To understand why, we must first understand what ammonia is and how it behaves in conditions far colder and stranger than anything we experience on our planet. Ammonia is a compound of nitrogen and hydrogen. On Earth, it exists mostly as a gas at standard temperatures and pressures. It has a sharp odor that most people recognize as the smell of cleaning products. In the cold reaches of space, ammonia can become a liquid. It freezes at about -78 degrees Celsius and boils at -33 degrees Celsius under Earth-like pressures. Those temperatures make ammonia alien to us but commonplace in the outer solar system. Titan, the largest moon of Saturn, is one such place where ammonia could be a liquid at least part of the time. Other moons and dwarf planets far from the warmth of the sun could host seas of ammonia mixed with water or other chemicals. Ammonia behaves in ways both similar to and very different from water. Like water, ammonia is a polar molecule. This means it can dissolve many substances, a key requirement for life chemistry. It can form hydrogen bonds, making it a good solvent for biochemical reactions. But ammonia has a lower surface tension and a lower heat capacity than water. This means it would transport energy differently. For a life form evolving in ammonia oceans, metabolism, growth, and movement would follow unfamiliar rules. If life could exist in ammonia, its chemistry would be slower and gentler. At the low temperatures where ammonia is liquid, chemical reactions happen far more slowly than in warm water. That could mean life there evolves at a glacial pace. What might take hours or days on Earth could take years or centuries in an ammonia world. Life might develop patience as a biological trait. Life forms could grow for decades before reaching maturity. Their metabolisms might be measured in centuries. Time itself would be experienced differently by ammonia life. Ammonia also has a remarkable ability to dissolve organic molecules and certain minerals. That means that in an ammonia ocean, the building blocks of life could move freely in ways similar to water, but in a chemical environment that would feel utterly alien to us. Proteins, enzymes, and genetic molecules might be replaced with entirely different structures adapted to ammonia's chemistry. Life could be built on nitrogen-rich compounds instead of carbon-based molecules, forming membranes, transport systems, and information carriers unlike anything on Earth. The energy sources for ammonia life would also be different. At the low temperatures of ammonia oceans, sunlight would be weak or absent. Life might rely on chemical energy from the ocean floor, heated by geothermal vents deep under the ice. It might harvest radiation from cosmic rays or nearby stars. In a world where warmth is rare, energy itself would be a treasure. Life might adapt to store energy for decades, moving only when necessary. The economy of living would be one of extreme efficiency. Ammonia life could take forms we can barely imagine. Without heat to power, rapid movement, creatures might drift lazily through their seas. They could resemble vast clouds of living ammonia, shaped by currents and chemical gradients. They might be slow and immense, or microscopic and numerous. Communication might be chemical rather than electrical or acoustic, and senses could work through detecting changes in chemical composition rather than sight or sound. Their perception of reality would be shaped entirely by their liquid world. A particularly fascinating possibility is that ammonia could mix with water to create an even more hospitable environment. Some scientists speculate that ammonia water oceans could exist beneath the icy crusts of moons such as Europa or Enceladus. Such mixtures lower the freezing point of water, allowing liquid to exist even where temperatures are far below freezing. This could create stable environments where life could thrive for eons, shielded from radiation and cosmic storms by thick layers of ice. Life in such oceans would be insulated, existing in quiet darkness and living in ways we can barely conceive. The idea of ammonia life also challenges our definition of habitability. For centuries, we have assumed that planets must be in the so-called Goldilocks zone, where liquid water can exist on the surface. But ammonia life would not need this zone. It could flourish in worlds far colder, far beyond the reach of Earth-like warmth. That means that habitable environments could be far more numerous in the universe than we once thought. They could exist wherever ammonia is liquid and other chemicals are present, in moons and dwarf planets scattered across the cold outer reaches of the solar system and beyond. Our search for life has focused mostly on finding water, but if we are serious about finding life beyond Earth, we must expand our vision. We must be willing to look for ammonia oceans, methane seas, or environments we have not yet imagined. The universe is unimaginably vast. Somewhere out there, a strange ocean of ammonia may swirl beneath an icy crust. Somewhere out there, life may exist that does not drink water, that does not breathe air, that does not grow in the way we understand. Ammonia life would not just be an alternative biology. It would be proof that life is not confined to the chemistry we know. It would mean that life is a broader phenomenon, a possibility that can take root wherever the right conditions exist. It would be an answer to the question of whether life is rare or common in the universe. It would mean life is not bound to the warmth of a blue planet, but can bloom in the darkness of a frozen world. And if such life exists, it would change everything we believe about our place in the universe. It would mean that life is not a miracle tied to a single chemistry, but a cosmic principle. That principle is persistence. Life finds a way not just in water, but in ammonia, methane, or worlds we have not yet imagined. Ammonia is strange to us now, but to a creature living in an ammonia ocean, it would be as natural as water is to us. That is the lesson of ammonia life. Life adapts to its home. It is not water that life needs above all else. It is the freedom to adapt to whatever liquid or energy surrounds it. If ammonia life exists, it would be life on a scale we cannot yet measure. It would be a testament to the creativity of the universe. It would be a sign that life is not rare but inevitable, and that possibility makes ammonia not just a chemical but a doorway to the unknown. Chapter 3. Can life form in liquid methane? Liquid methane is one of the strangest substances in the solar system. It flows in rivers and fills lakes on Saturn's moon Titan. To us, it is utterly alien. On Earth, methane exists as a gas under ordinary conditions and is mostly known as a fuel or greenhouse gas. But far from the warmth of our sun, methane can become a liquid at temperatures around -198 degrees Celsius. That is almost unimaginably cold. To put it into perspective, the coldest temperature ever recorded on Earth was about -89 degrees Celsius. Titan is more than twice as cold. That means that methane on Titan behaves like water on Earth. It falls as rain, gathers in lakes, flows in rivers, evaporates, and condenses in a cycle that is remarkably similar to Earth's hydrological cycle. That makes Titan a world unlike any other we have explored. The idea that life could exist in liquid methane stretches the boundaries of our imagination. Life on Earth depends on liquid water. Water dissolves chemicals, facilitates complex reactions, and transports nutrients. But methane is chemically very different. It is a hydrocarbon, not a polar molecule. It cannot dissolve salts or sugars in the way water does. That means any life based on methane would require entirely different biochemistry. It would not be water-based life wearing a new coat. It would be life born of a different chemical world altogether. The first challenge to imagining methane life is temperature. At -198 degrees Celsius, chemistry slows dramatically. Reactions that take microseconds in warm water would take centuries or millennia in methane at Titan's temperature. For life to exist there, its chemistry would have to be adapted to work extremely slowly or rely on processes we cannot yet conceive. Metabolism might operate on timescales unimaginable to humans. Life could grow at rates so slow we could not measure it in a human lifetime. The very notion of a life cycle might be different. Birth, growth, reproduction, and death might stretch over centuries or even millennia. Another challenge is the chemistry itself. Methane does not dissolve most substances we consider essential for life. Yet in methane oceans, certain hydrocarbons do dissolve. Titan's lakes are not pure methane, but mixtures of methane and ethane. These liquids could serve as solvents for an alien biochemistry. Life in such a world might be based on entirely different molecules than the proteins, carbohydrates, and lipids we know. Its building blocks might be based on hydrogen and carbon arranged in structures that are stable at low temperatures. Such structures could store information, carry energy, and build membranes in ways we cannot yet imagine. One of the most intriguing possibilities is that methane life might not even breathe or eat in ways we recognize. On Titan, chemical energy could be more important than sunlight. There is little light at Titan's distance from the Sunday energy. Sources for life might come from the breakdown of organic molecules in the lakes or from chemical gradients beneath the surface. These processes could be extremely slow, meaning life there might exist in a state of patient persistence. It might not rush to reproduce or grow, but instead conserve energy, living for centuries in a steady state. Life in liquid methane would look and behave unlike anything on Earth. It might not have cells in the form we know, but instead membranes made of exotic hydrocarbons. These membranes would be thick and stable at low temperatures, protecting internal chemistry from the harsh environment. Metabolism might occur within suspended droplets, tiny microcosms drifting in Titan's seas. Life forms might be microscopic, floating in currents, or vast drifting mats spanning lakes. They might communicate chemically rather than electrically, sensing their world through changes in composition rather than light or sound. Their perception of reality would be shaped entirely by the properties of methane. Titan's environment presents other fascinating possibilities. The thick nitrogen atmosphere and constant haze of organic molecules raining down from the sky create a kind of slow chemical factory. Methane, ethane, and other hydrocarbons rain down from clouds and collect in lakes. Complex organics form through photochemical processes driven by sunlight and Saturn's magnetic field. These processes could provide the raw materials for life, creating an ecosystem powered by chemistry rather than sunlight. Titan's atmosphere and lakes could be a laboratory for a kind of biology we have never seen. If life exists in liquid methane, it would challenge everything we think we know about habitability. For centuries, our search for life has been focused on finding water. We have assumed that liquid water is essential, but methane life would prove that life does not need water at all. It could exist in places we have dismissed as barren. The habitable zone would no longer be a narrow band around a star, but could include vast worlds of ice and hydrocarbons far from warmth. That expands the possibility of life across the universe dramatically. The consequences of discovering methane life would be profound. It would prove that life is not a rare accident. It would mean that life is a natural outcome wherever the right conditions exist. It would mean that life is not a product of a single chemistry, but a principle that can take root in completely different environments. Life in liquid methane would be proof that biology is not confined to water and warmth, but can thrive in the cold and darkness of alien worlds. We cannot yet know what methane life would look like. It might be slow-drifting colonies, enormous single organisms spanning lakes, or microscopic creatures hidden in the haze. Their entire biology would be written in a chemistry foreign to us. But that strangeness is precisely what makes the idea so compelling. If life can exist in liquid methane, it means the universe is more inventive than we can imagine. It means that somewhere out there is a world where life does not breathe air, does not drink water, and does not grow in the way we know. Titan stands as a tantalizing possibility. Its rivers and lakes of methane might not be barren. They might be the cradle of a strange, slow life, drifting beneath a sky tinged orange by haze. If we ever visit Titan and explore its lakes, we may discover a biology unlike anything we have ever known. That would change the way we see life, not just on other worlds, but here on Earth. Life in liquid methane would show that life is not rare, fragile, or limited to a single formula. It would show that life can adapt to the coldest, most alien conditions. It would show that the universe is not just a place where water exists, but a place where chemistry itself creates endless possibilities for life. And that would be the greatest discovery of all. Chapter 4. What if life lived in clouds, not oceans? The idea that life could exist in clouds is both strange and beautiful. On Earth, we associate life with solid ground or liquid oceans. Life clings to surfaces, burrows into soil, swims in water, or grows in sunlight. But the atmosphere itself is a vast, unexplored world. Venus offers perhaps the most tantalizing possibility. Its surface is hot enough to melt lead and pressure so extreme it would crush any human or Earth life. Yet high above that hellish surface there is a layer of clouds that is much more temperate. Around 50 kilometers above the ground, the temperature and pressure are surprisingly similar to conditions on Earth. In that zone, Venus is warm, with breathable pressure and a thick cloud layer. These clouds are made of sulfuric acid and thick chemicals toxic to us. But to life adapted to Venus, they could be a home. Cloud life would be completely different from any life we know. Instead of crawling over surfaces or swimming in oceans, these organisms would float. They might drift endlessly, suspended in droplets of acid or chemicals. They would live not in solid ground, but in the air itself, sustained by chemical gradients, sunlight, or perhaps unseen currents. Their bodies might be designed for buoyancy. They could be balloon-like structures filled with gases that keep them afloat. Their outer layers might be protective membranes resistant to acid, shielding delicate internal structures. Life in clouds might not even have a fixed shape. Organisms could change their form as they move through different layers of the atmosphere. Venus's clouds are thick and dynamic. Winds whip around the planet at speeds over 300 kilometers per hour. Cloud life would need to cope with constant movement. It might drift passively on the currents, or actively control its position, using tiny adjustments. It might harvest energy from sunlight, filtered through thick layers of clouds. Photosynthesis, as we know it, might be impossible in Venus's clouds, but chemical processes could substitute. Acid droplets raining down from above could contain nutrients that cloud life harvests. Lightning storms could produce energy for life. Chemical interactions between sulfuric acid and atmospheric gases could provide fuel. The very concept of life in clouds challenges our definitions of habitat. We think of life as rooted in something stable, with food nearby. Cloud life would be suspended in a vast and shifting environment. It would be nomadic in the most extreme sense, carried by winds that circle the planet every few days. For a cloud organism, home would not be a place but a layer of atmosphere. Survival would mean adapting to constant change. Life in clouds might be small and simple or vast and complex. Microscopic organisms might drift like spores, invisible to the naked eye but abundant in their millions. Larger organisms might be enormous, drifting colonies shaped like jellyfish or balloons spanning hundreds of meters. They could form living swarms that cluster together for protection or reproduction. They could communicate chemically, exchanging nutrients or information through trails of vapor. They might use light to signal one another in the thick haze. One of the most fascinating aspects of cloud life is its possible biology. Without solid ground or liquid water as a base, life would have to rely on chemistry that works in gases and droplets. Its cells might be suspended within acid droplets, with membranes that can survive both dryness and acidity. Its metabolism might be driven by the breakdown of sulfuric acid or other compounds in the atmosphere. It might feed on chemicals drifting in the clouds or on microscopic particles suspended in the haze. Cloud life would also live in a world of extremes. Venus is a world of constant storms and endless motion. The clouds themselves are dynamic, changing shape and density. A cloud organism might drift into a zone of higher acidity and adapt its outer layer. It might ride up and down in the atmosphere to follow nutrients. It might have life cycles measured not in days but in months or years, living slow and drifting endlessly. If we found life in clouds, it would change how we understand habitability. We search for life in oceans and soils, but a living atmosphere would show that life does not need solid ground or deep seas. It would mean that every planet with an atmosphere could be a home for life. That would expand the possible places for life in the galaxy far beyond what we now imagine. Searching for cloud life would be difficult. We could not simply land on Venus and dig. We would need aerial probes that float for years, sampling the atmosphere and searching for signs of life. Such probes would have to survive acidity, high winds, and constant motion. They would need to detect life that is small, drifting, and possibly very different from anything we know. Life in clouds would be an existence of constant drift. It would live in the interplay of chemistry, wind, and sunlight. It would be a form of life that thrives without solid ground, without oceans, without anything we think of as a home. It would be a life built entirely for the air, shaped by the currents of a living atmosphere. If Venus holds such life, it would mean that life is more adaptable than we can imagine. It would mean that life can exist without oceans, without soil, without even a surface to call home. It would mean that life can take root in the sky itself. That would transform our understanding of life and show that the universe has not just one way of living, but many. Cloud life would be proof that life is not defined by where it lives, but by the chemistry that sustains it. It would show that life can drift on winds for centuries, that it can survive in acid, that it can find meaning in constant motion. It would be a form of life unlike any other, and discovering it would change everything we know about biology and the nature of life in the cosmos. Chapter 5. Could silicon life replace carbon life? When we think of life, we usually think of carbon. Carbon is the backbone of life on Earth. It can form long chains and complex molecules that are perfect for building cells and proteins. Carbon is versatile, stable, and abundant. But the universe is vast and strange, and there is no rule that says life must follow the same path it did on Earth. Silicon is one of the most promising alternatives. Silicon is in the same chemical family as carbon. It can form bonds and chains similar to carbon, and it is the second most abundant element in Earth's crust. That makes it a strong candidate for alternative life chemistry. Silicon life would be very different from carbon life. Silicon atoms form stronger bonds at higher temperatures, which means silicon life might thrive in worlds too hot for Earth life. Instead of liquid water, it might need molten rock or high-temperature gases. Silicon compounds are more stable at extreme temperatures. This means silicon life could survive on worlds that are volcanic or close to their stars. A silicon-based organism might be built like living stone. Its structure could be crystalline, strong, and durable. Instead of soft cells and membranes, it might have shells of silicates or structures similar to quartz. These shells could protect against extreme heat or radiation. Silicon life might not be flexible like carbon life. It might grow slowly and live for centuries or millennia. Its metabolism could be based on chemical reactions in molten rock, or even gases like silane or silicon hydrides. Silicon life might not even look like what we think of as life. It could resemble living crystals or rocks. These beings might not move in the way animals do, but instead grow in place, spreading slowly like a living mountain. They might communicate through changes in structure or light patterns in their crystals. Silicon life could be capable of storing information in the arrangement of its crystalline structures, almost like a living hard drive. One of the challenges for silicon life is chemistry. Silicon bonds are not as flexible as carbon bonds. They tend to form solids rather than liquids. That means silicon life would be less adaptable in some ways. But it could thrive where carbon life cannot. Worlds with extreme heat, high pressure, or chemical compositions unfriendly to carbon could be homes for silicon life. This expands the possibility of where life could exist in the universe. The environments where silicon life might exist are breathtaking. Imagine a planet with seas of molten rock and air filled with exotic gases. Imagine mountains that are alive, growing crystal structures that shimmer and change color. Imagine a world where life is a slow geological process rather than a biological one. In such a place, living organisms could be inseparable from the planet's surface. They could be entire landscapes rather than small creatures. Silicon life might feed differently too. Instead of eating or photosynthesizing, it might consume heat or radiation. It might harvest energy from volcanic activity or chemical gradients in its environment. Some scientists suggest silicon organisms could feed on minerals in rocks or use the energy of planetary magnetic fields. That would make them not just different in structure, but in how they survive and interact with their world. The lifespan of silicon life might be extraordinary. Without the wear and tear of soft organic tissues, they could survive for thousands of years. They might grow slowly, layer by layer, like stalactites in a cave. Their evolution might be measured in geological epochs rather than generations. A silicon organism could survive conditions that would destroy any carbon-based creature in seconds. If silicon life exists, it would completely change our understanding of biology. We would learn that life does not require the delicate balance of water and carbon chemistry. Life could be built from stone shaped by heat and pressure. It would mean that life could exist in places we currently consider hostile and barren. Silicon life could exist on worlds with crushing gravity, searing heat, or toxic atmospheres. It would mean the universe has many more homes for life than we ever imagined. Searching for silicon life would be challenging. It might not move or breathe or show signs we recognize. It could exist as crystal structures blending into landscapes. We would need to look for patterns in minerals or unusual energy flows. We would need to rethink the very definition of life. Silicon life would be proof that life is not a single recipe but a vast set of possibilities. It would be life that thrives in extremes that would kill carbon creatures. It would be life shaped by heat and stone, not water and flesh. And finding it would mean opening our minds to the countless forms life could take in the universe. If life can take the form of stone, then every volcanic world, every molten planet, every world with heat and pressure could be a living world. That possibility changes everything. It means life could be far more common than we imagine and far stranger. Silicon life would be a testament to the creativity of nature. It would show that life is not just a thing but a process that can adapt to anything the universe offers. Chapter 6. What if life fed on radiation, not food? When we think of life, we usually imagine eating and drinking. Food gives us energy and nutrients to live and grow. On Earth, all life depends on some form of chemical energy, usually stored in organic matter. But what if there was another way to survive, another way entirely different from anything we know? Imagine a creature that does not eat in the conventional sense, but instead absorbs energy directly from its environment. This energy could come from light, radiation, heat, or even the invisible streams of particles that flow through space. Such beings could survive without food or water in places that seem utterly lifeless. Radiation is everywhere in the universe. It is the energy emitted by stars, by cosmic rays, by gamma bursts, and by magnetic fields. It reaches us constantly, yet it is invisible to our eyes. We cannot see it, but it is all around. For most life on Earth, radiation is dangerous, but there is no rule that says all life must avoid it. Life could evolve to use radiation as its source of energy, in the same way plants use sunlight. Such creatures would be living solar panels drawing their power from starlight or cosmic energy. One of the most likely forms of radiation-based life could be photosynthetic, but far beyond what we know. Our plants absorb visible light and turn it into energy. Radiation life could absorb entire spectrums of electromagnetic radiation. They could live in ultraviolet light X-rays, or even gamma rays. They might have structures designed like microscopic antennae tuned to specific wavelengths. This would allow them to feed directly from the light of a nearby star or from the diffuse glow of cosmic background radiation. Radiation feeders could exist in the harshest places. They might live close to stars where radiation is intense or deep in space where there is no atmosphere. They might even survive inside clouds of cosmic dust or in the magnetospheres of giant planets. Radiation-feeding life would be adapted to survive without water or organic matter. Their metabolism could be entirely based on absorbing energy from electromagnetic waves and converting it into sustaining processes. The biology of such creatures could be extraordinary. They might not have mouths or digestive systems. Instead, they could have surfaces designed to capture radiation. They might glow or change color as they feed. Their bodies could be crystalline or metallic to enhance energy absorption. Some could resemble floating sheets or membranes drifting in space. Others might be dense spheres covered with structures designed to trap every particle and photon that passes by. Radiation life might not have the same need for movement as other organisms. They could simply drift in space or anchor themselves to a surface bathed in radiation. They could survive on constant streams of energy without needing to hunt or forage. Their lifespans could be enormous. With a steady supply of radiation, they might survive for centuries or even millennia. They could grow slowly, absorbing energy and converting it into more complexity over time. The environments where radiation life could exist are breathtaking to imagine. Worlds close to powerful stars could be alive with creatures feeding on intense light. Clouds of dust around young suns could be filled with drifting life forms. Even the void of interstellar space could be home to creatures that harvest cosmic rays. These beings might live in places where nothing else could survive. They might be the ultimate explorers drifting between worlds on streams of radiation. Radiation-based life might communicate in ways that seem impossible to us. They could emit patterns of light or radiation to send signals. They could sense changes in radiation around them as a form of perception. They could use the language of energy rather than sound or movement. For them, radiation would not only be food but information. If life can feed on radiation, it changes how we search for life. We would need to look for unusual patterns of radiation in space. We might detect life by spotting structures that absorb or emit radiation in unnatural ways. Radiation life might be invisible to our telescopes unless we know exactly what to look for. That means they could be all around us without us even noticing. Radiation life would be a revolution in biology. It would prove that life does not require organic matter or water to survive. It would prove that life can adapt to the most extreme environments. Such life would open a new chapter in our understanding of the universe. It would mean that life is not a rare miracle, but a universal phenomenon that can take shapes beyond our imagination. The existence of radiation life would mean life could survive in places where we never thought it possible. It could thrive in the cold void of space near dying stars in the heart of nebulae, or in the radiation belts of giant planets. It could be the most ancient form of life in the universe, drifting silently between galaxies. Radiation life would be a testament to the boundless adaptability of life and the vast possibilities that the cosmos holds. Chapter 7. Could ice worlds hide living oceans? The idea that life could hide beneath the surface of frozen worlds changes everything we know about where life can exist. When we look at planets and moons in our solar system, we often see them as barren and lifeless, especially those covered in thick ice. Yet beneath that frozen crust, there may be entire oceans of liquid water kept warm by hidden forces. These oceans could be vast and deep, stretching for hundreds of kilometers under miles of ice. They might be insulated from the cold of space and from deadly radiation by the ice above them. These hidden oceans could be among the most promising places to search for life beyond Earth. Take Europa, a moon of Jupiter. Its icy surface is covered in ridges, cracks, and chaotic terrain that suggests a subsurface ocean in motion. Beneath that shell of ice may lie more water than all of Earth's oceans combined. The heat comes not from the sun but from tidal forces. Europa's gravity is pulled and stretched by Jupiter and other moons, producing friction deep inside. This friction creates heat enough to keep water in liquid form beneath the ice. That hidden ocean could be a habitat. It could contain minerals and energy sources that life could use to survive. Enceladus, another icy moon of Saturn, gives even more reason to wonder. Cassini spacecraft detected geysers of water vapor and organic molecules shooting from cracks in its icy surface. These plumes suggest that Enceladus has a warm ocean beneath the ice, and that it might contain the chemical ingredients needed for life. If life exists there, it could be hidden from view under layers of ice but accessible to those willing to search deep enough. The concept of life under ice is both ancient and revolutionary. Earth itself holds examples of life thriving in extreme cold beneath ice. In Antarctica, under kilometers of ice, there are lakes such as Lake Vostok that remain liquid and host microbial life. These life forms survive without sunlight using chemical energy from minerals in the water and heat from the Earth's core. If life can survive there on Earth, then similar environments on other worlds could also be alive. Ice worlds might host life that is completely unlike anything we know. They could be microbial or much larger. They could float freely in subsurface oceans or anchor themselves to mineral-rich surfaces. They could feed on chemical compounds rising from the ocean floor or harvest energy from thermal vents. Their ecosystems could be closed and self-sustaining, existing in total darkness. In those worlds, life would not depend on sunlight but on chemical and thermal energy. The ice covering these worlds is more than a barrier, it is a protector. It shields the oceans below from cosmic radiation and the harsh conditions of space. It creates a stable environment where life could persist for millions or even billions of years. For creatures living beneath the ice, the world above would be a frozen ceiling lit only by faint light filtered through cracks or by bioluminescence from organisms themselves. Life under ice could be mysterious and strange. Creatures could have evolved without eyes, relying on other senses to navigate. They could use sound vibrations, chemical gradients, or electromagnetic signals to communicate and find food. They could have slow metabolisms adapted to cold and darkness. They could be simple, single-celled organisms or complex, multi-celled creatures adapted to life in a hidden ocean world. The discovery of life in a subsurface ocean would change everything we know about biology and the search for life. It would mean life can exist without sunlight, without air, and without the open sky. It would expand the definition of habitable worlds far beyond what we once imagined. Every icy moon in our solar system and beyond could be a potential home for life. Exploring these worlds will be difficult. Drilling through kilometers of ice to reach an ocean is a challenge unlike anything we have done before. But missions are being planned to explore Europa Enceladus and other icy bodies. They will search for chemical signs of life and try to answer the question of whether life hides beneath the ice. If life is found beneath the frozen surface, it would be proof that the universe is filled with hidden possibilities. It would mean that life does not need warm surface oceans to thrive. It could exist in darkness under ice for eons. Ice worlds could be living worlds, and beneath their frozen shells, entire oceans could be teeming with life unknown to us. The idea changes our vision of the universe. Worlds that appear cold, barren, and lifeless might in fact be the quietest cradles of life. They might be homes to ecosystems that have never seen the light of day and that have existed far longer than life on Earth. Ice worlds could be the hidden hearts of life in the cosmos and the key to understanding what life really is. Chapter 8. What if life exists in the vacuum of space? The vacuum of space is the coldest, emptiest place we can imagine. It has no air, no liquid, and no warmth. It is a place where temperatures drop to nearly absolute zero, where radiation from stars streams endlessly, and where there is no atmosphere to shield anything from deadly cosmic rays. At first glance, it seems impossible that life could survive in such a place. Yet the question of whether life could exist in the vacuum of space challenges everything we think about biology and survival. Life on Earth depends on a delicate balance of air, water, nutrients, and temperature. Even the most extreme environments on Earth still have some of these things. But space has none. It is a place of pure emptiness. No air to breathe, no water to drink, no soil to anchor life. The very idea of survival in space seems absurd, and yet scientists have found organisms that come astonishingly close to defying those limits. Tardigrades, microscopic creatures known as water bears, are famous for their ability to survive in extreme conditions. They have been sent into space and exposed to the vacuum and intense radiation. Many survived. They did so by entering a state called cryptobiosis, in which their metabolism nearly stops. Their bodies dry out and they curl into tiny spheres. In this state, they can endure extreme temperatures, radiation, and the vacuum of space for years. Tardigrades prove that life can adapt in ways we might never expect, and that the vacuum of space might not be an absolute barrier to life. If microscopic organisms can survive in space even temporarily, the question emerges: could there be life that evolved to live there permanently? Could there be creatures designed to drift through the void, to survive without air or water, without warmth or a planet to call home. Such life would have to be unlike anything we know. Its biology would need to be built for a world without atmosphere, without gravity, without a defined home. One possibility is that such creatures would be extremely small and simple, able to survive on energy from radiation or cosmic particles. They might exist as single cells or even simpler structures that require no complex body systems. They could have protective shells or membranes that resist radiation and shield them from extreme cold. They could float through space like seeds on the wind carried by solar radiation and magnetic fields from star to star. Another possibility is that spacefaring life might be much larger. They could be immense drifting organisms that harvest energy directly from starlight or cosmic radiation. Their bodies could be translucent membranes stretching across vast distances, capturing energy and nutrients from the void. They could use magnetic fields to navigate and survive. Such life forms would live entirely in space, never touching a planet and never needing an ocean or atmosphere. Life in the vacuum of space would not depend on water in the traditional sense. It might rely on exotic forms of chemistry, entirely alien to us. It could feed on subatomic particles, plasma streams, or the radiation of distant stars. Its metabolism could operate on principles we cannot yet imagine. These beings could have evolved in deep space for millions of years, and might drift unseen between solar systems as silent travelers of the cosmos. If such life exists, it might already be among us. Microscopic spores could travel through space carried by meteorites or dust. They could land on planets or moons and survive in dormant states for eons before finding an environment where they could grow. This is one of the ideas behind panspermia, the hypothesis that life can travel between worlds on rocks or cosmic dust. If panspermia is true, life in the vacuum of space might be not only possible but common. Detecting life in space would be an immense challenge. Such life could be invisible to our eyes and our instruments. It might be so small that it blends with cosmic dust or so alien that we do not recognize it as life. We would need entirely new tools to search for it. Telescopes designed to detect unusual radiation patterns, spacecraft designed to capture tiny drifting particles, and experiments to study the survivability of organisms in space will all play a role. The idea of life in the vacuum of space expands the boundaries of the possible. It challenges the notion that life must be confined to planets, oceans, and atmospheres. It opens the possibility that life could be drifting through the galaxy as unseen travelers riding the currents of the universe. Life could exist in the emptiest places, not in spite of the vacuum, but because of it. The void could be not a dead zone, but a vast ocean teeming with drifting organisms beyond imagination. If life exists in space, it would mean the universe is far stranger and more alive than we ever imagined. It would mean that life does not need a planet to survive, that the cosmos itself could be a habitat. The vacuum of space would not be emptiness, but a home, and the vast stretches between stars could be filled with life quietly drifting on journeys across eternity. Chapter 9. Could plasma be alive? Plasma is one of the 4 fundamental states of matter, along with solid, liquid, and gas, but it is also the most common state of ordinary matter in the universe. Stars, the sun, lightning auroras, and even some nebulae are made of plasma. It is a state where atoms are so energized that electrons are stripped away, leaving a soup of charged particles. Plasma flows, it glows, it dances with light and energy. It shapes magnetic fields and moves across vast distances in space. This makes it one of the most mysterious and dynamic materials in existence. The idea that plasma itself could be alive challenges everything we think we know about life and biology. On Earth, life is always built on matter that has solid structures that hold cells together. Plasma does not have a fixed shape or structure in the way solids and liquids do. It is constantly moving, changing, and responding to electromagnetic forces. If life is defined as the ability to grow, reproduce, respond to the environment, and maintain some internal order, plasma could theoretically meet some of these criteria. Plasma is incredibly complex. It can form filaments, sheets, and loops. It can store energy and move in ways that resemble biological processes. This raises the question, could plasma form patterns or systems capable of sustaining something like life? One way to imagine plasma life is to think about networks of charged filaments stretching across the cosmos. These filaments could behave like living tendrils responding to the magnetic fields of stars and planets. They could grow and change shape over time. They could interact with other filaments to exchange energy or information. These plasma systems might operate on timescales so vast they are difficult for us to perceive. To them, a human lifetime would be a blink of an eye. They could live for millions or even billions of years, flowing and reshaping themselves continuously. Plasma life would not rely on water or organic chemistry. Its chemistry would be electromagnetic. Its metabolism could involve capturing energy from stars or cosmic radiation and converting it into patterns of motion and organization. Reproduction could happen by splitting into separate plasma structures or by transferring energy patterns across vast distances. Communication could be carried out through electromagnetic pulses, light waves, or changes in magnetic fields. These forms of life would be utterly alien to us, not built of cells or DNA, but of pure energy and motion. The idea of plasma as a living entity is not purely science fiction. There are natural plasma processes in the universe that exhibit surprising complexity. Auroras on Earth respond dynamically to solar winds in ways that resemble living organisms sensing and reacting to their environment. Plasma filaments in nebulae form intricate and stable patterns that persist for centuries. Some scientists have proposed that the universe itself could be permeated by a kind of cosmic plasma consciousness, where life exists on scales far beyond the planetary or biological. Plasma life would challenge how we define life. It would force us to think beyond the confines of carbon chemistry. It would mean that life is not necessarily tied to molecules or cells, but can emerge wherever there is energy and the right conditions for order to form. This would expand the search for life far beyond planets and moons. The glowing gas around stars, the magnetic fields of galaxies, and the vast clouds of plasma in interstellar space could all be potential habitats. If plasma life exists, it could be ancient beyond imagination. Plasma structures in space can last for millions of years. They could carry information and memories across vast distances. They could have evolved slowly over the lifetime of galaxies. They might be the most widespread form of life in the universe, invisible to us because we are not equipped to see it. The question then becomes, how would we detect plasma life? We would need to look for patterns in space that cannot be explained by ordinary physics. We might search for repeating structures or signals in plasma clouds. We might study the behavior of auroras or solar flares for signs of intentional organization. It would require new instruments and new ways of thinking. Plasma life would exist at the boundary of physics and biology, and would challenge our deepest assumptions about existence. If plasma can be alive, it means the universe is not merely a collection of inert matter and energy, but a living, vast network of dynamic systems. Life would not be an exception, but a fundamental part of the cosmos. Stars and galaxies themselves could be part of a greater living network. Plasma would be not just the medium in which life exists, but life itself flowing through the universe in glowing patterns of unimaginable scale and beauty. The possibility that plasma could be alive changes everything about the way we search for life. It means life could be woven into the fabric of the universe. It means life could exist in places we never dreamed possible. It means that somewhere out there among the stars and the glowing clouds of charged gas, there might be beings made not of flesh or water, but of pure light and energy, quietly living across the cosmos. Chapter 10. What if life exists as pure energy? Energy is the most fundamental substance in the universe. Everything we see, everything we touch, and everything we are is made of matter and energy. Matter itself can be thought of as a form of energy bound together in particular structures. But what if life could exist not as matter at all, but entirely as energy itself? Such a possibility changes everything we know about biology, existence, and the limits of life. Pure energy life would not need cells, DNA, or physical form. It would be existence as patterns of energy. These patterns could be stable arrangements of photons, electromagnetic fields, or other exotic forms of energy. They could move through space without needing a body. They could change shape instantaneously and travel across vast distances at the speed of light. Such beings would not be bound by the slow timescales of biology. Their perception of time could be radically different. A second for them might stretch into centuries or collapse into an instant. The first challenge in imagining energy life is understanding what it means to be alive without matter. On Earth, life depends on chemistry. It builds structures that can reproduce and adapt. But energy itself can also form patterns. Plasma fields pulsate. Light waves interfere to form stable structures. Electromagnetic fields twist and loop. If such patterns could self-organize in complex ways, they could meet the criteria we use for life. They could store information, reproduce themselves, and adapt to changes in their environment. These beings would not eat in the way we understand. Their sustenance would come from absorbing energy directly from their surroundings. They could feed on starlight cosmic radiation or the energy of gravitational waves. Their metabolism would be a process of energy conversion rather than digestion. They might exist in regions of the universe where energy is abundant, such as near stars inside nebulae, or in the intense radiation fields near black holes. Communication for energy beings would be instantaneous and multidimensional. They could use electromagnetic waves, light pulses, or quantum entanglement to exchange information. Their language could be a flow of energy patterns beyond our ability to perceive. They could communicate across light years without delay. Their perception of reality could be based entirely on the interaction of energy fields, rather than sensory input like sight or sound. The lifespan of pure energy beings could be beyond our comprehension. They could persist for as long as the energy patterns that sustain them remain stable. Some could exist for millions or billions of years. Others might exist for only the briefest flash of light. For them, death could be simply the dispersal of their energy pattern into the surrounding space, but their essence might persist as part of the cosmic energy web forever. If life as pure energy exists, it might already be all around us without our knowing. The universe is filled with energy fields that we cannot directly perceive. Cosmic background radiation, plasma waves, magnetic fields, and light itself could be part of a hidden living system. We might pass through living beings every time we step outside without realizing it. The universe might be a vast living entity with countless forms of energy life woven through it. The possibility of energy life forces us to rethink the boundaries of biology. Life would no longer be something that exists only in the narrow conditions of planets or water, but a possibility anywhere energy flows. It could exist in the heart of stars in the deep vacuum of space, or inside the quantum foam at the smallest scales. Energy life could be the most ancient and widespread form of life in the universe. Detecting such beings would be a monumental challenge. They might not interact with matter in ways we can measure. Their presence could be revealed only through subtle changes in energy patterns or unexplained fluctuations in electromagnetic fields. Discovering them would require entirely new methods of observation and new ways of thinking about what life is. It might require us to expand our definition of life to include patterns and processes beyond physical form. If pure energy life exists, it could change humanity's place in the cosmos forever. It would mean that life is not an accident of matter, but a fundamental feature of the universe. It would mean that consciousness and awareness could exist without bodies. The universe itself might be alive in ways we have never imagined. It might be filled with beings of pure light drifting through space, weaving the fabric of reality into something living. The idea that life could exist as pure energy is both thrilling and humbling. It means that life is not bound to our senses, our biology, or even our understanding of physics. Life could be far stranger and more beautiful than we can imagine. Somewhere in the vastness of the cosmos, there might be entities of pure light and energy, aware and conscious, moving through the universe with a freedom beyond human understanding. Chapter 11. Would we even recognize life if we saw it? When we think about life, we imagine things that move, breathe, eat, reproduce, and respond to their environment. Life for us is tied to biology. It is tied to cells, DNA, metabolism, growth, and reproduction. These are the things we have learned from studying Earth. But the universe is unimaginably vast, and the conditions elsewhere could be so different that life might not look anything like what we know. If that is the case, we may not even recognize life if we saw it. Recognition depends on expectations. We expect life to have certain signs because all life we know comes from a single origin on Earth. This life is carbon-based, it needs liquid water, it has DNA and cells, and it breathes or consumes energy. But those signs are just one possibility. The universe might contain life forms that exist in completely different ways. They might be based on elements other than carbon. They might not need water. They might not move in ways we understand. They might not even exist in three-dimensional space as we know it. A being could be a structure of energy, a pattern of radiation, a cloud of plasma, or an arrangement of magnetic fields. It could exist in the fabric of space-time itself, without a physical body. To us, it might appear as nothing at all. We might pass by and never know it is there. If life is fundamentally about self-organization and information processing, then these forms could be as alive as any animal, plant, or microbe. But they would not signal their existence in ways we expect. Even if we saw such life, we might not know it. It might not move in ways that are obvious. It might not change visibly over time. It might not produce chemical signatures that we can detect. We could mistake it for a rock, a cloud, or random noise. Our perception is shaped by our senses and instruments. We look for life the way we understand it, but that may blind us to life that exists in forms beyond our comprehension. Recognition of life requires defining what life is. That is a harder question than it seems. Scientists debate the criteria. Some focus on metabolism, some on reproduction, some on evolution. Others suggest that life is simply any system capable of processing information and maintaining a boundary between itself and its environment. By this broader definition, life could be almost anywhere and almost anything. A storm on a distant planet, a crystal growing in a cave, a self-sustaining magnetic swirl in space could be alive. If we ever encountered alien life, it might challenge the very meaning of life. We might meet beings that communicate in ways we cannot understand, or that exist on timescales far beyond ours. They might perceive the universe in ways we cannot imagine. They might be aware in a form that has no equivalent in human experience. Their life could be beyond recognition, not because it is hidden, but because it does not conform to any pattern we have learned to identify as living. There is also the possibility that life is so different it could be invisible to all our instruments. We explore the universe with telescopes and probes that detect light particles, radiation, chemicals, and heat. But if life does not interact with these in expected ways, we might never see it. It could exist in dimensions we cannot measure, or at scales too small or too vast for us to detect. It could be a silent life that drifts unnoticed through the cosmos. Our inability to recognize alien life may also limit our ability to search for it. We design experiments based on what we know. We look for water signs of carbon chemistry and atmospheric gases we know are linked to life on Earth. But these searches may miss entire realms of life that do not fit these criteria. The real diversity of life could be far beyond what our instruments are designed to find. The question of whether we would recognize life if we saw it is also a question of humility. It reminds us that life may be far stranger than we can imagine. It reminds us that our knowledge is shaped by the narrow window of human experience. If we expand our minds and redefine life, we may open ourselves to discoveries that transform our understanding of the universe. If we find life that we cannot recognize, it will force us to rethink everything. It will force us to rethink biology, physics, and philosophy. It will make us question our place in the cosmos and our understanding of existence. Life may be the most profound mystery of the universe, and our ability to recognize it may depend on our willingness to question everything we know. The universe may be filled with life forms all around us that we do not see. They could be there in forms so alien they escape our definitions. They might live in silence or in forms we cannot detect. Recognizing life may require us to become something more open-minded than we have ever been. We may have to learn to see without expecting to see, and to understand without expecting to understand. The search for life is not just a search for biology. It is a search for possibility. It is a challenge to our imagination. It is a challenge to our senses and to our ideas of what is real. Whether we would recognize life if we saw it is not just a question of science, but a question of perception, understanding, and openness to the unknown. If life is something broader than we think, then the universe may be alive in ways we have never considered. And the greatest discovery of all may not be finding life, but learning to recognize it in its infinite diversity. Chapter 12. What if life never needed water to begin with? When we look for life, we instinctively look for water. Water is the basis of all life on Earth. It is the medium in which cells exist. It transports nutrients, carries away waste, and facilitates chemical reactions. Every living thing we know depends on water. It is the foundation of our biology and the foundation of our search for life. But what if water is not the only foundation that life could rest upon? What if water is just one possibility and not the universal requirement we have assumed? If we imagine a universe where life never needed water, we open a door to an extraordinary range of possibilities. Life could have begun in ways we cannot even imagine. It could be built on entirely different chemistry. Life could be based on ammonia or methane, on silicon or metals, on plasma or pure energy. If life does not need water, then the criteria we use to define life must expand beyond the boundaries of Earth. Water has certain advantages that make it ideal for life. It dissolves many chemicals, it remains liquid across a wide temperature range, and it has a unique ability to support complex chemistry. But those advantages are specific to Earth conditions. Other planets and moons offer environments where water is rare or absent. If life exists in those places, it must have adapted to conditions we would call extreme. Life could be built on solvents that behave very differently than water. Ammonia could be one option, methane another. These chemicals would create environments with different temperatures, pressures, and chemical behaviors. Life there would not just look different, it would operate on different principles. If life never needed water, it might not be liquid at all. It could exist as a solid crystalline structure, as a floating cloud of gas, or as a current of plasma. It could survive in extreme temperatures and pressures where water could not remain liquid. This would mean life could exist in places we have never considered habitable. It could thrive on moons in the outer solar system, on planets far from their suns, in environments of ice, rock, gas, and radiation. Life without water could be radically different in its metabolism. Without water to carry nutrients and remove waste, life might use entirely different processes to maintain itself. It could consume energy in ways we cannot imagine. It might not have cells at all, but exist as networks of molecules or as patterns of energy. Its reproduction could be unlike anything we know. Instead of dividing like a cell, it might grow by accreting matter from its environment or by reorganizing existing structures. The origin of such life would also be profoundly different. On Earth, life began in water-rich environments with cycles of energy and chemistry that eventually produce self-replicating molecules. But if water is not necessary, then life could begin in environments that are dry, cold, or even chaotic. It could begin in the atmosphere of a gas giant in clouds of ammonia or methane. It could begin in the mineral depths of a rocky planet where heat and chemical energy drive strange forms of chemistry. If life never needed water, then it could be much older and more widespread than we imagine. Water-based life is limited to places where liquid water exists, and those places are rare. But if other solvents or other forms of existence can give rise to life, then the conditions for life could be everywhere. Life could be a common feature of the universe, not the exception. The cosmos could be filled with forms of life that we do not recognize because they do not live in water. This possibility changes how we search for life. It suggests that our focus on finding water may limit our discoveries. We must broaden our approach to look for signs of life in environments we have not yet explored. This means designing experiments that detect different kinds of chemistry that could support life. It means being open to signs that life exists in forms we do not understand. The implications of life without water go beyond science. It changes our understanding of what life means. If life can exist without water, then it is not a special accident of Earth, it is a possibility built into the fabric of the universe. It means life is more resilient, more diverse, and more surprising than we have imagined. It means life could be as varied as the planets and stars themselves. It also challenges our sense of place in the universe. We imagine life as something fragile, dependent on a narrow set of conditions. But if life never needed water, it could thrive in unimaginable environments. Life could exist in places where we would not expect it at all. The universe could be alive in ways we have not even begun to conceive. If water is not necessary, then the search for life becomes infinitely richer. We no longer look only for Earth-like worlds. We look for the possibilities that lie in the chemistry of alien worlds. We look for life in the cold clouds of Titan, the dense atmosphere of Venus, the icy depths beneath Europa's crust, the radiation-filled void between the stars. We look for life everywhere because life without water could be everywhere. Perhaps the greatest lesson of imagining life without water is humility. It reminds us that our knowledge is limited by what we know. It reminds us that life could be stranger and more wonderful than we have dared to imagine. Water is our lens for understanding life. But it is not the only lens. The universe is vast and full of mystery, and life may exist in forms beyond our ability to perceive. If life never needed water, it means that life is not a singular story told only on Earth. It is a possibility woven into the universe itself. The story of life could be as infinite as the cosmos. The greatest discovery may not be finding life, but realizing that life is possible in ways we have never dreamed. The question of life without water is not just a scientific question. It is a question that touches philosophy, imagination, and the limits of human understanding. It asks us to imagine a universe in which life is not rare and fragile, but abundant and diverse. It invites us to see life as a possibility that extends far beyond our own experience. It invites us to dream of a universe alive in ways we cannot yet comprehend. If life never needed water, then life is not a mystery to be solved. It is a reality to be discovered again and again across the cosmos.